Hello, I'm Sheldon Axler, the author of Linear Algebra Done Right. This video discusses part 2 of the section of the book titled Positive Operators and Isometries. In this video, we will be focusing on isometries. An operator S is called an isometry if the norm of S of V is equal to the norm of V for every vector V. In other words, an operator is an isometry if it preserves norms. I would like to make a comment here about terminology. Many books actually have two different words to describe what we are calling an isometry, depending upon whether the vector space in question is real or complex. In the real case, isometries are often called orthogonal, and in the complex case, isometries are often called unitary operators. To me, it's much cleaner and easier to use just one word, isometry, to denote both cases. The word isometry comes from the Greek isos, meaning equal, and the Greek word metron, meaning measure. Thus, isometry literally means equal measure. That's a good description of the equation, the norm of S of V equals the norm of V. Let's look at some examples of isometries. For our first example, suppose lambda is a scalar. Then lambda times the identity operator is an isometry if and only if the absolute value of lambda is equal to 1. Please pause the video and verify this statement. It's quite easy. For our second example, suppose now we have n scalars, lambda 1 through lambda n, all with absolute value 1, and we have an operator S on V that satisfies the equation S applied to Ej is equal to lambda j Ej for some orthonormal basis E1 through En of V. Suppose we take a vector in V. We can write it as a linear combination of the basis vectors. Because we have an orthonormal basis, we actually know what the coefficients are. They're shown in the first equation here. We also have a formula, based on the Pythagorean theorem, for the norm of V, again from the coefficients. That's the second equation that you can see here. Now, let's apply S to the first equation above so that we get a formula for S of V, just using linearity. It's the formula you see now. S applied to each Ej is equal to lambda j Ej, so we get the equation now displayed. And we can use this equation with the Pythagorean theorem again to calculate the norm of S of V squared. It's, again, the sum of the squares of the absolute values of the coefficients as shown here. Now, look at the two equations highlighted now in red, and you can see that the norm of V is equal to the norm of S of V. In other words, S is an isometry. The next result gives several conditions that are equivalent to being an isometry. Here's what this result says. Let S be an operator on V. Then the following are equivalent. Condition A is that S is an isometry. In other words, S preserves norms. Condition B, as you can see, is that S preserves inner products. It may be a little surprising to you that preserving inner products is equivalent to preserving norms. Condition C is that if we have any orthonormal list of vectors, E1 through En in V, and apply S to that list, we again get an orthonormal list of vectors. Condition D is there exists at least one orthonormal basis, E1 up to En of V, such that when we apply S to it, we again get an orthonormal list. Condition E is that the adjoint of S times S is equal to the identity operator. Condition F is that S times the adjoint of S is equal to the identity operator. Condition G is that the adjoint of S is an isometry. In other words, the equivalence of A and G means that S is an isometry if and only if its adjoint is an isometry. And finally, condition H says that S is invertible and the inverse of S is equal to the adjoint of S. Now let's discuss the proof for this result. We'll prove that all of these items are equivalent by the chain of implications that you can see in front of you, starting with A implies B, implies C, etc., ending up with H implies A. So let's begin. First, we'll suppose that A holds, meaning that S is an isometry. Strangely, this proof breaks into two cases depending upon whether the scalar field is real or complex. Let's look at the real case. So suppose F is the set of real scalars. For every u and v, we have the following formula for computing the inner product. The proof of this is obtained by simply expanding the right-hand side using the usual rules. For example, write u plus v squared in norm as u plus v, inner product u plus v, and expand, and you'll see that this is true. This does require the scalar field to be real, because at one point in the proof of this, we need to interchange the inner product of u with v to have that equal to the inner product of v with u. If we were dealing with a complex case, we'd have to add a complex conjugate. At any rate, you should pause the video, verify this equality. Okay, now that you're back, because S is an isometry, that's our assumption, we can rewrite the right-hand side of the equation as follows. This is because the norm of u plus v is equal to the norm of S applied to u plus v, because S is an isometry, and similarly for S applied to u minus v. Now we get the next equation simply by the linearity of S. And finally, we again use the equation that gives the inner product just in terms of norms, but this time applying it to S of u and S of v instead of u and v. Now look at the two equations highlighted in red, and we can see that S preserves inner products. The proof in the complex case, which you should do yourself because we're not going to do it here, is very similar. You just need to find a formula for expressing the inner product of u with v just in terms of norms. If you get stuck, please look at the book, but make sure you work that out. We have now shown that A implies B. Let's wipe away that proof so we have room for the proof that B implies C. So now suppose that B holds, meaning that S preserves inner products. We need to prove C. To do that, suppose E1 through En is an orthonormal list of vectors in V. Then the list S of E1 up to S of En is also orthonormal, because one determines orthonormality by looking at S of Ej, inner product S of Ek. By our hypothesis B, that's equal to Ej, inner product Ek. And because the E's are orthonormal, that's equal to 0 if j is not equal to k, and 1 if j equals k. In other words, the list S of E1 up to S of En is orthonormal. That proves C, and we have completed the proof that B implies C. Clearly C implies D, because C says something is true for every orthonormal list, and D says there's an orthonormal basis for which it's true, and because every finite dimensional inner product space has a basis that's orthonormal, we have D. Let's wipe away the proofs showing now so that we have room to prove that D implies E. So now suppose that D holds, and by D we have an orthonormal basis E1 up to En, such that S of E1 up to S of En is also orthonormal. Let's look at the inner product of S star S Ej with Ek as shown on the left. We can flip the S star to the other side, getting the right-hand side of the equation that's displayed now. Now this is equal to the inner product of Ej with Ek because both sequences, E1 up through En and S of E1 up through S of En, are orthonormal. Every vector in V can be written as a linear combination of the basis vectors E1 up through En. And that implies by linearity that the equation above, holding just on the basis vectors, actually holds for all vectors. In other words, we get the last displayed equation, S star S applied to U, inner product with V, is equal to U, inner product V. And that, holding for all U and V, implies that S star S is the identity operator. In other words, E holds. This completes the proof that D implies E. Now let's erase the second column so that we have room for the next set of implications. We want to prove that E implies F. E states that S star S is the identity operator. In general, an operator and its adjoint do not commute under multiplication. However, in this special case they do. That's a special case of the result that if we have two operators, S and T on V, then TS equals the identity implies ST equals the identity. To remind you of the proof of this, the reason it's true is that the equation TS equals the identity implies that S is one-to-one or injective and T is onto or surjective. Both S and T in this case are operators from a finite dimensional vector space to itself. So having just one of injectivity or surjectivity gives the other one for free, and that's what gives us ST equals the identity. Applying that result to the operator where T is equal to S star gives us that E implies F. So now let's suppose that F holds, meaning that S times the adjoint of S is equal to the identity operator. We want to prove G. So let's take a vector V and look at the norm of S star of V squared. That's S star of V inner product with itself. Flip the S star on the right to the first slot, getting the second equation shown here. Now our hypothesis is that S star is the identity, so we now get the third equation showing that this is equal to V inner product V. And of course, V inner product V is equal to the norm of V squared. Now if we look at the first equation and the last one, both highlighted in red, we see that those two equations show that S star is an isometry. In other words, we have proved that F implies G. Let's again wipe the second column clean so that we can go on to the next set of implications. Suppose now that G holds, meaning that S star is an isometry. We have proved through the chain of implications that A implies E and A implies F. Let's use that, but with S replaced by S star, because our assumption is now that S star is an isometry. Using that, and using the result that S star star is equal to S, we conclude that SS star is equal to the identity operator, and S star S is equal to the identity operator. The two equations above imply that S is invertible, and that the inverse of S is equal to the adjoint of S. In other words, we have proved that G implies H. We are now ready to prove the last implication. Suppose that H holds, meaning that S is invertible and the inverse of S is equal to the adjoint of S. Thus S star S is equal to the identity operator. Suppose V is a vector, then the norm squared of S of V is equal to S of V inner producted with S of V. Flip the S in the second slot on the right into the first slot, getting the second equation shown here. Now use our hypothesis that S star S equals the identity operator to rewrite that as V inner product V, which of course is the norm of V squared. If we now look at the first and last parts of this chain of equations, highlighted in red, we see that it says that S is an isometry, showing that A holds. In other words, we have proved that H implies A, completing our chain of implications, and completing the proof of this result. There were a lot of steps to this result, so this is a good time to pause the video, make sure you can do all these steps. If not, please check with the book. Our last result in this video gives a complete description of isometries on complex inner product spaces. We should note that this result is false on real inner product spaces. In a later video, we will give the correct result for real inner product spaces. Our result states that if V is a complex inner product space and S is an operator on V, then the following are equivalent. Condition A, S is an isometry. Condition B, there is an orthonormal basis of V consisting of eigenvectors of S whose corresponding eigenvalues all have absolute value 1. Let's look at the proof of this result. Suppose condition A holds, meaning that S is an isometry. As we proved in our previous result, this implies that S star equals the identity and S star S equals the identity. In particular, that means S star equals S star S. In other words, S commutes with its adjoint, thus S is normal. The complex spectral theorem gives a description of normal operators on complex inner product spaces of finite dimension. It says there's an orthonormal basis, E1 up to En of V, consisting of eigenvectors of S. By the way, this is where we use the hypothesis that V is a complex inner product space. Let's fix an integer j from 1 to n and let lambda j be the eigenvalue corresponding to the eigenvector E sub j. Then, the absolute value of lambda j is equal to the norm of lambda j times E sub j. That's because the norm of E sub j is equal to 1. And lambda j E sub j is equal to S E sub j because E sub j is an eigenvector with eigenvalue lambda j. So we have this equality now shown. And S is an isometry, that's our assumption here, so the norm of S of Ej is equal to the norm of Ej. And of course, the E1 up to En was an orthonormal basis, so the norm of each Ej is 1. Looking at the first and last equations, now highlighted in red, we've shown that each eigenvalue of S has absolute value 1. Thus, condition B holds. We've proved that A implies B. We showed earlier that B implies A. We did that as an example, so that completes the proof of this result. This concludes part 2 of the video on positive operators and isometries. If you see a small picture of a slide in the upper left corner of this slide, then you can click on it to get to the next video.